All right, chemistry, this is your video lecture for chapter 22, section 1. This will be the second half of your lecture for this section. In the previous lecture video, we covered these first two objectives. We were able to explain what a nuclide is and describe different ways nuclides can be represented. We were also able to define and relate the terms mass defect and nuclear binding energy. Today, we're going to finish off the objectives for this particular section by being able to explain the relationship between the number of nucleons and the stability of nuclei, as well as being able to explain why nuclear reactions occur and how to balance a nuclear equation. All right, to that extent, we'll skip to where we left off last lecture, and here we go. Nucleons and nuclear stability. The stable nuclei cluster over a range of neutron-proton ratios that is referred to as the band of stability. What this is getting at is the way nuclei construct themselves is based on a neutron-to-proton ratio, not an absolute number of nucleons, not an absolute number of protons or an absolute number of neutrons, but the ratio of neutrons and protons to one another. When you're looking at atoms that have low atomic numbers, for example, numbers 1 through 10, so it'd be hydrogen, helium, lithium, and so on, the most stable nuclei for those particular atoms are those with a neutron-to-proton ratio of about 1 to 1. An example would be helium. Helium, by definition, has 2 protons, and the most stable form of helium has a mass number of 4. So that means, using what we learned last chapter, that this particular type of helium has 2 protons and 2 neutrons. It's a 1-to-1 ratio, making this low atomic number atom stable. But as that atomic number increases, when you get close to things like iron and even higher up into lead, for example, that stable neutron-to-proton ratio isn't 1 to 1 anymore. It actually slowly changes to about 1.5 to 1, okay, 1.5 to 1. For example, we have lead 206 here. Now, if you don't have a periodic table in front of you, lead has an atomic number of 82. And if we were to have a 1-to-1 ratio, that would be 162 for the mass number here. But we don't have a 1-to-1 ratio of neutrons to protons. We have closer to that 1.5 to 1 ratio. So we're essentially adding another 40. Yeah, that would be the 0.5 of the atomic number. We're adding another 40, and we're going to get up to that 206 mark.
The strong nuclear force that holds nucleons together operates over very short distances. It is very strong for adjacent protons and neutrons, such as A and B, but rapidly diminishes for more distant nucleons, such as A and C. In contrast, the electromagnetic force which pushes nucleons apart remains potent over long range. The strong nuclear force has to combat the electromagnetic force. For nuclides with low atomic numbers, the extra strong nuclear force supplied by neutrons can balance out the electromagnetic repulsion between protons. At very low atomic numbers, roughly 1 neutron per proton is needed for atomic nuclei to be stable. As the atomic number increases on the scale, 1 1/2 neutrons per proton are needed. If the atom has less than this number of neutrons per proton, the nucleus will become unstable. After a certain point, the number of nucleons becomes too large to be held together by the strong nuclear force, and all nuclei are unstable, regardless of the number of neutrons.
And here's that graphic for the band of stability that we just talked about. Again, notice down here at the very near the origin of this graph, meaning at the lower atomic numbers, things like hydrogen and helium and lithium, the stable nuclei cluster around the 1-to-1 ratio line, which is here represented by a dashed red line. But as the number of as the atomic number goes up, we get larger and larger atoms, larger and larger nuclei. This best fit line actually starts to curve up and into the 1.5 to 1 ratio, which here is represented by this solid red line. Now, the band of stability, the reason that is the case, can be explained by the relationship between the nuclear force, okay, we've established that we're talking about the strong nuclear force here, and the electrostatic forces between protons. Remember, protons are all positively charged, and according to the normal rules regarding electrostatic forces, there should be a massive repulsive force there. So we have the strong nuclear force, which is an attractive force, and the electrostatic force here, which is a repulsive force, interacting with one another. This band of stability results from that relationship. Stable nuclei, by the way, tend, not always, but tend to have even numbers of nucleons. All right, so when you add up the number of protons and neutrons, generally speaking, it's going to be an even number. Now, according to the nuclear shell model, based on this tendency, nucleons exist in different energy shells or different energy levels within the nucleus. The number of nucleons that represent a completed nuclear level are those even numbers, and they tend to be 2, 8, 20, 28, 50, 82, and 126. And yes, you will need to remember those. You'll need to remember that it's representative of the nuclear shell model. You'll need to remember that stable nuclei tend to have even numbers of nucleons. And then you'll have to remember this progression of magic numbers. 2, 8, 20, 28, 50, 82, and 126.
When nuclei have protons and neutrons in amounts equal to their magic numbers, the nuclei are highly stable. Nuclei with both protons and neutrons are especially stable. 2 is the lowest magic number, so helium-4, with 2 neutrons and 2 protons, is the simplest nucleus with magic numbers for each nucleon. Helium-4 is highly stable compared to neighboring nuclei, such as lithium-6 or hydrogen. The next magic nucleus is oxygen-16, with 8 protons and 8 neutrons. Calcium is also a very stable nucleus, with a magic 20 protons and the possibility for a magic 20 or magic 28 neutrons. Tin is a heavy element with 56 protons, making it magically stable. Bismuth has 126 neutrons, also making it magically stable. Lead has 82 protons, making this nucleus magically stable. A major isotope of lead also has 126 neutrons, making it doubly magic. Lead is one of the most massive nuclei that is stable. Many heavier nuclei decay to become lead.
Moving on to nuclear reactions themselves. Unstable nuclei, all right, so that's going to be nuclei that don't follow at higher atomic numbers, the 1.5 to 1 neutron to proton ratio. So unstable nuclei undergo spontaneous changes that change their number of protons and neutrons. Again, why would they undergo a spontaneous change? Because they're unstable. They don't fall into that 1.5 to 1 neutron to proton ratio. So it's kind of like standing a pencil up on edge. That's not the most stable form of that pencil to be in. So it will spontaneously fall down into that more stable, flat on the table form. The same thing with these unstable nuclei. They will emit protons and neutrons until that ratio reaches that best fit curve that we see in the band of stability. So a nuclear reaction is a reaction that affects the nucleus of an atom. Okay, so we're not necessarily talking about the number of electrons, okay, and things like chemical bonding. We're talking specifically about the nucleus itself. For example, if we were able to fuse beryllium and helium, in order for this to be a successful nuclear reaction and have stable products, we would yield a carbon atom, right? Because we have 2 protons from helium, 4 protons from beryllium. That would give us a total of 6 protons. That is going to land us on atomic number 6, which is carbon. Now, the most stable form of carbon is going to be carbon-12, because this is a low atomic number here. This is number 6. That's a very low atomic number. So according to the band of stability, the ratio of neutrons to protons need to be 1 to 1. So in order to have 1 to 1, you're going to have 6 protons, therefore 6 neutrons. Add that together for a mass number of 12. Well, if you look at the mass number of this beryllium and this helium that we used in this reaction, the total mass number is 13. So even though we have a very stable form of carbon, we need to do something to account for that. Apparently, it's a neutron that was ejected from this nuclear reaction. So we simply write lowercase n subscript 0, representing its charge, or representing the number of protons, positively charged particles there. And then the superscript 1, which again represents the mass number. It's the overall mass of that particle. And this is how we represent a neutron. You may have heard this term specifically with regard to alchemy, but a transmutation is a change in the identity of a nucleus as a result of the change in the number of protons. So this is very difficult to do in a controlled setting, but if you can change the number of protons, this is considered a transmutation.
The alpha decay of polonium-210 produces an alpha particle and lead-206. The total atomic mass of the products, 206 for lead and 4 for the alpha particle, add up to 210, the atomic mass of the polonium nucleus. The total positive charge is also the same on both sides of the equation. The positive charge is tracked with the atomic number. 84 protons in polonium is the same amount as 82 protons in lead and 2 protons in the alpha particle. Beta decay obeys the same rules. When carbon-14 decays into nitrogen, there is a beta particle emission. The total atomic mass of the particles does not change, since electrons are very light compared to nucleons. When we add the charge of the electron, -1, to the charge of the nitrogen nucleus, 7, the result is the charge on the carbon nucleus, 6.
So when it comes to balancing a nuclear equation, there are a few things that we need to do. First thing you want to look at is the mass and atomic numbers. So the mass number and the atomic number. The rule here is the total of the mass numbers on both sides of the equation have to be equal, right? Conservation of mass. Also, the total number of atomic numbers must also be the same on both sides of the equation. Again, conservation of mass. If the atomic number of an element changes, remember that the identity of that element changes as well. So if I give you a simple notation, and throughout that chemical reaction, the number of protons changes, as your product, you're going to have to represent that change in identity by using the different or appropriate elemental symbol. Continuing to look at balancing nuclear equations, we want to determine how nuclear reactions change mass and atomic numbers. There are a couple of different types of things that we're going to see and use to help us balance these types of equations. There's a beta particle. So if a beta particle is released, we represent it by E sub -1 super 0. Yeah, this is essentially an electron. It has no mass. Notice the mass number is 0, and it has a negative charge. If a beta particle is released, the mass does not change because it essentially has no mass, but the atomic number increases by 1. You might ask, why would the atomic number increase by 1? The number of protons didn't change. I understand that, but realize we've lost a negative charge. And so when you subtract a negative number, you actually result in gaining a positive. So we've actually transmuted one of those neutrons into a proton by removing negative charge. Similarly, or I guess conversely, if a positron is released, and this has essentially no mass, so that superscript is 0, but the subscript is positive 1 because there is a positive charge with this particular particle. Again, the mass number doesn't change. That mass number is 0, so the overall mass number does not change, but the atomic number will decrease by 1 because you're losing one positive charge, and you will actually turn one of the protons in that nucleus into a neutron. So you're actually losing one proton, even though a proton is not being ejected from the nucleus. You're simply losing that positive charge. If a neutron, right, no charge, so the subscript is 0, but the superscript is 1 because a neutron has a mass of 1, AMU, right, relative atomic mass. The mass number will decrease by 1. Again, you're losing that neutron, but the atomic number does not change. There's no change in charges here. Electron capture does not change the mass, but it decreases the atomic number by 1. And so if you have a beta particle and you're actually combining that beta particle with whatever nucleus you already have, the mass number isn't changing. That beta particle has essentially no mass, but it does have a negative 1 charge, so it's going to neutralize one of the positively charged protons. Not the mass, just the charge, and so you will essentially be losing one proton, so the atomic number will decrease by 1. If there's an emission of an alpha particle, if you remember from the previous chapter, then an alpha particle has the mass of a helium atom. Okay, it was 4 times that of a hydrogen atom, was the way the book described it. The mass number is going to decrease by 4 because the mass number is 4. You're emitting that, therefore losing it. You're also going to decrease the atomic number by 2 because, again, this alpha particle is being emitted. It's being lost. That subscript, that positive charge, is 2. You're losing 2 positive charges, and so you're going to be neutralizing 2 of your protons, therefore decreasing the atomic number by 2. When a positron and an electron collide, energy in the form of gamma rays is generated. You may have heard of these gamma rays. It's not something that we encounter very often in normal common life. This is one of the reasons. We have some special subatomic particles that need to come into contact in order for these things to be generated, and that's why we don't see a whole bunch of Bruce Banners and Hulks running around. I do have one sample problem for you. I want you to be able to identify the product that balances the following nuclear reaction. So I have polonium-212, and I want to emit an alpha particle. If I have polonium and it emits an alpha particle, okay, it loses an alpha particle, what element is the other product? Now remember, the total mass number and the total atomic number have to be equal on both sides. That's going to be the big factor in being able to complete this particular type of problem correctly. So again, mass number on both sides as well as atomic number on both sides must be equal. Now we're starting with a mass number of 212, and obviously we're losing a mass number of 4, so whatever element I have as a result is going to have a mass number of 208. Similarly, I'm starting with an atomic number of 84, it's polonium, but I'm losing 2 protons, and so my atomic number is going to go down by 2. And that's going to leave me with an atomic number of 82. So what I simply do is I look through the periodic table and I find the element that has an atomic number of 82, and I describe it as having a mass number of 208. So looking at the periodic table, we see that the element that has an atomic number of 82 is lead, and it has a mass number of 208. So the balanced nuclear equation is polonium-212 emitting an alpha particle, resulting in lead-208. All right, chemistry, this will be the last lecture for this section. I will see you next period.